welcome to the lecture 11. So far we have done that limit state of collapse, flexure or bending. Today we shall start learning shear. So, our today's lecture limit state of collapse, shear, and how shall we resist shear? We do it, we are doing the problem on beam. If we take a simply supported beam, maybe it is resting over brick wall. Okay. So, let us take a simply supported beam resting over a brick wall. If we have uniformly distributed load, let us apply the uniformly distributed load. We have the bending moment. To resist bending moment, what we have to provide? We have to provide longitudinal reinforcement. This is for longitudinal reinforcement. To resist flexure or bending. In addition to that, we can have that shear and diagonal stresses. We can have shear and diagonal stresses. So, we can have the diagonal tension if we take one element, and we can have diagonal tension, so that the crack it will just split. And other thing also possible, the diagonal compression. Okay. So, I think it should be the other way, this particular one. So, we can have the diagonal compression, and similarly we can have tension in beams, that if we take these are the longitudinal reinforcement. So, we can have tension. So, this is, and we have to resist these cracks, and how shall we make it? The shear failure, we can have different types shear failure. This is due to say shear tension, this is one case, this could be due to shear tension. We can have shear bending, this type of say your case shear bending. We can have, there is one the shear bond, applied load here, and there is a shear bond, that also we can resist, and we can have that shear compression. So, these are the 4 different cases possible. If we just go back once more, let me just go back once more. So, we can have shear tension, the crack pattern may look like this. Then we can have shear bending, we can have that due to bond, that also we shall take care separately, that bond. Today we shall consider, we shall take care that how to resist shear and shear compression. So, you can see this one shear compression. What we can do here, that we can do it here itself. We use tie or we use stirrup. How it looks like? The stirrup is made this way, That means, you take a bar and you start bend, so that you can make this type of thing, and generally it comes if we take the bar, which can come, and this one the longitudinal one. We are looking from this side, so this is your longitudinal bar, and from the center line of longitudinal bar, which will come in the range of say 8 phi, 8 times the diameter of this stirrup. The stirrup can have diameter say 6 millimeter, it can have diameter 8 millimeter, 10 millimeter, 12 millimeter, and the other side also we have two sides. So, other side also it will come say 8 phi, depending on the link that it can hook. So, we can have 6 phi also. So, we have to provide this reinforcement. Who will resist this? Out of these 4 sides, who will resist shear? The shear will be resisted by these two members. So, we have to provide that both sides the stirrup, that the stirrup contains 2 legs, we call it 2 legs. So far the longitudinal reinforcement concern for bending, we have used say 3 20 millimeter diameter bar, or 4 20 millimeter diameter bar, or 5 20 millimeter diameter, the number of bars and the diameter. But here what we do, we provide, maybe we could say like this 8 Tor, that it means that 8 dia Fe415, with this symbol we designate, and let us say at the rate of 150 millimeter center to center. So, here we are not specifying number of bars, instead we are specifying the spacing of those stirrups, and here in addition to that we provide, to make it very clear, we say 2L. So, we provide like this 8 Tor 2-legged, it is 2-legged, and at the rate of say 150 millimeter center to center. So, since we are having 2 legs both sides, so we can have 3-legged also, we can have 4-legged also. So, depending on the shear, that whatever shear that force applied, so that you have to resist. So, you have to provide number of bars. And the different types of bars that stirrups could be, one simple one, the what we generally provide, this one. If we need more, then we can have single link like this also. That means, we are providing reinforcement say and this bar will come like this. Then we shall consider this one as 3-legged, whereas this one 2-legged. So, ASV, the area of steel, if we designate, so far we have done AST, the tensile reinforcement, longitudinal one, and here we specify as say ASV. This is your shear reinforcement. So, for 2-legged, it should be twice times pi by 4 times say, let us say phi square for 2-legged. If it is 3-legged, then 3 into pi by 4 times phi square. So, this is your that how we will calculate that ASB. So, we have to provide ASB and the spacing which we specify as SV, SV spacing of stirrups. So, we have to provide that stirrup spacing and stirrup reinforcement, the diameter, and we have choice that whether we have to provide 2-legged or 3-legged or 4-legged. Generally, most of the cases for beam we find that 2-legged sufficient. So, in that case we shall increase the diameter. We can start with 8 millimeter. If it is not sufficient, then we can go to 10 millimeter diameter, and but most of the cases we shall restrict ourselves to 2-legged stirrups only. Now, what about the shear stress? The shear stress distribution for rectangular section, it comes parabolic. In the elastic stage, say we are getting in this pattern, ultimate stage that this portion becomes linear. But in our calculation, we shall not use this formula, or we shall not use this stress distribution. What our IS code says, let us find out. So, we shall take care that nominal shear stress, according to IS 456, that our code says that we shall not go to that parabolic distribution. Instead, we shall take this nominal shear stress, and you will find out in this clause, the clause 40.1 IS 456 2000. The nominal shear stress in beams of uniform depth shall be obtained by tau v, that is the shear stress developed, equal to Vu. Vu is the design shear force. Vu is the design shear force. So far we are always in our calculation in limit state design, we are taking care of that you would say design load, the design moment, design force, assuming that we have already multiplied that one with the proper partial safety factor for forces, that already we have taken care of, that 1.5 times or 1.2 times depending on the situation. That we shall take care separately when we shall go for actual problem, practical problem. We shall take a problem separately, because right now we are doing component wise. We are taking how to take care say beam flexure, now how to take care say beam that say shear, similarly say for column, for slab, then footing, staircase, all the components we shall do it separately. We are doing individual. Then we shall take care one problem, say building, and then we shall analyze and then solve the problem and then design. There we shall do that proper multiplication of that factors, all those things we shall do. Right now we are assuming that the final that Vu that is given to us. So, here that Vu the force, so Vu the shear force, that is the design shear force, divided by B that width of the beam, and D that is the effective depth. So, we shall get the shear stress tau v. We shall get the shear stress tau v, that our code says that do not go for your that parabolic distribution, all those things. So, we can take the nominal shear stress and we can do our calculation. So, Vu the shear force due to design loads after proper multiplication of different factors, if it is dead load, live load, earthquake load, or say your wind load, whatever it is, that we do not know. After taking care of that load, we are getting that Vu. So, we have to design that for that Vu. The B breadth of the member, which for flange section shall be taken as the breadth of the wave, that is clearly mentioned, that if it is a flange section, that means T beam. So, we shall not take the BF, that width of the flange, we shall take the width of the wave, and D is the effective depth, and D is the effective depth. So, how can we resist that beam shear. If we take care, this is your longitudinal bar, this one also longitudinal bar, and we have to, and this is the assumed crack, say from the support generally it happens because shear force is maximum near the support. So, the crack, all those things due to shear you will get near the support, and most of the cases you will get this type of diagonal cracks, and that we have to resist by stirrups. So, we have different components. The bent up tension bar, let us say we can provide that beam this is your say beam. What we can do, if we take say simply supported beam, generally say simply supported beam that bending moment 0 that in the support. So, that means we do not need that much of your say tensile reinforcement. What we can do, the bar which is coming from this side, the bar which is coming from this side, because we are assuming the tensile force, the tensile stress in the bottom in the most of the cases, and then we can take these bars say 45 degree and we can go up the bent up bars. So, bent up tension bar. So, which we have mentioned here that bent up tension bar, that means this tension bar here I am specifying this tension bar which is going this way. This is one bar, this is one bar. So, that means this bar is coming from this side, then it is bent going upward and then this way. So, that means it will also resist certain portion of part of the shear. The second one, system of vertical stirrups. The system of vertical stirrups means these bars which we have to provide, and the third one, system of inclined stirrups. The stirrups also we can provide in an inclined manner in this fashion. So, we can have three different components: bent up tension bar, system of vertical stirrups and system of inclined stirrups. So, shall we go the other one? Okay. So, let me give you some time if you would like to take it. So, this is the general format, but generally most of the cases nowadays we do not go for bent up bars, we do not go for say inclined one. Most of the cases we use for detailing purpose, because reinforced concrete detailing is also one important aspect in reinforced concrete design. So, in that case what we do, we take care the bars that one just straight, we do not bend bars because it will take a lot of time also. That is why we always nowadays we use say straight bars. In a very rare case we use the say bent up bars. So, what we have to provide? We have to provide that say longitudinal reinforcement that one straight, we are not bending those bars. Inclined bars we hardly we use it, most of the cases we use straight, that is say vertical stirrups only, not inclined stirrups. So, we have to provide this say vertical stirrups and the longitudinal reinforcement. So, the shear forces are resisted by combined action of concrete and shear steel. Shear steel is nothing but the stirrups. So, it is resisted by concrete and shear steel. So, resistance in concrete is due to the combined effect of three factors. So, we are now taking care say there is one concrete and your say other one, that is your say stirrup. So, concrete has three different factors. One which we designate by say VCZ, shear carried by uncracked section 20 to 40% of total shear in compression. So, this it means that uncracked section, we shall take care that uncracked section. We can draw a figure. So, if we take care this bar, the uncracked portion is at the top, because in the compression side. So, this one we can say that VCZ is the uncracked portion. So, this one will be, this portion of the concrete will be taken care of by concrete only, and that one this we are taking VCZ. The next one we have that VA, shear carried by aggregate interlock across the diagonal crack, aggregate interlock. Even it cracks, there is an aggregate interlock, and that one will be taken care of almost say 3 to 50%. So, this is called VA. So, we can say VA means here, this is VA, okay. And what about the third component? The third component here VD, shear carried by dowel action of longitudinal tensile steel. That means, tensile steel also will take certain percentage, say 15 to 25% of the case. So, we shall get that 15 to 25%. So, that is your say VD. So, VD will be taken care of by this longitudinal reinforcement. So, this is VD. So, VCZ, VA and VD. So, shear carried by concrete, that summation of all those three. So, we can write down here. So, VC equal to VCZ plus VA plus VD. VC equal to VCZ plus VA plus VD. But we do not know all the different components. We do not know all the different components. So, we have to find out VC. Now, VU, that shear force due to design load. So, we can say Vs, that means for which we have to provide the stirrup. So, Vs equal to Vu minus Vc. So, Vc, what we are doing, that whatever the force applied, we are not designing that, we are not providing stirrup for the whole shear force that which is applied. Instead, we are taking care of, that means we know that certain portion will be taken care of by concrete, which has three different parts. So, VCZ, VA and VD in combination, which comes say VC. If we can find out VC, so we can subtract that VC from the VU, the remaining balance VS, if it is there at all. For that, we have to provide the shear reinforcement. However, we provide nominal shear reinforcement even if we get that less than that, VU if it is a less than VC. The VC, that means a critical shear force, the concrete can take care, even if it comes less, even then we provide nominal shear reinforcement. So, what I have told, the total shear to be carried. So, V concrete plus V stirrup. So, Vc plus Vs or Vu, whatever. Now, what we shall find out, the tau c, this is I have just simply given from the table 19 of IS 456, part of table. There are so many other things, say M15 also there, M30, lot of others, and also it goes beyond 1.25% of the steel. So, to find out that Vc, we do not know how shall we find out, because we do not know what are the different components for say dowel action, we do not know what is the aggregate interlock, how much will be the for that compression part. instead of that, depending on the percentage of longitudinal steel, the tensile steel, we shall get the tau c. So, tau c is the critical shear stress the concrete section can take, which is dependent on the percentage of longitudinal tensile reinforcement, and which is given in table 19 of IS 456. So, because already you have designed for flexure where you are providing the tensile reinforcement. So, on the basis of that you know what is the how much is that percentage of tensile reinforcement, and depending on that for the grade of concrete you can find out what is tau c. So, that means we are not getting directly the component basis, we are getting lump sum, okay, this much we can get that which will give us that Vc. So, Vc is nothing but tau c Bd. So, Vc will be nothing but tau c Bd, and remaining portion we can take care by the stirrup. So, this one you will get it in IS 456, that table 19. There is one more table, that is your say table 20, where we shall get say maximum shear stress. We are getting that one say shear stress, that nominal shear stress or tau c, we are getting the critical shear stress, and the other side that we are having the tau c max, that which is called the maximum shear stress for a particular grade of concrete. So, which comes as say for M15 it is 2.5, M20 2.8, M25 3.1, M30 3.5, like that. It means that if we have a section say tau v, we can get the tau v. So, Vu is the design force. So, tau v equal to Vu by Bd, that is the nominal shear stress. So, Vu we are getting from our calculation after giving that proper factor, all those things. B we know that width, D already we have given that D, because depth of the section already we have done it for the flexure point of view. So, I can get tau v. So, this tau v should not be more than that your say tau c max, which is given in table 20 of IS 456. So, table 20 IS 456 which is given here, it says that M20 that we shall get 2.8 maximum, 2.8 Newton per square meter. So, if it is more than 2.8, then we have to redesign the section, that means we have to change the section, we have to increase the depth. That means, though we have done it for say from the flexure point of view, even then from the shear point of view it fails, and therefore, we have to change the section, we have to increase the depth. So, that means it is the beam is shear dominated. So, that means this is the another aspect that we have to consider, that means only flexure is not sufficient. So, we have to take care that, and there also we have to increase the depth of the section. So, now one more thing I have to tell, because these are the things which we should know when we are doing the design. So, according to IS 456, what is the maximum pacing of shear reinforcement? That is there is a limit that it should not be, shall not exceed 0.75 d for vertical stirrups. When we are providing that vertical stirrups, it should not be more than 0.75 d. D is the effective depth, and for inclined stirrups say at 45 degree, it should not exceed d, that effective depth. And where d is the effective depth under consideration, that means where we are considering in, and also one more clause, that in no case shall the spacing exceed 300 millimeter. So, even then say your depth is more, say 0.75 d. So, you are getting say something say 500 is the effective depth, that means your spacing will be more than 300. So, in that case it should be restricted by that 300 millimeter. So, in our design calculation, whenever we do the design, so these are the different restrictions that we have to follow, and on the basis of that only we can design. Now, let us find out the shear capacity. So, shear capacity of stirrups. And let us say this is your longitudinal bar, and there is a crack say at 45 degree, the diagonal tension, and we have to resist so the diagonal tension. So, we have to provide the stirrups. So, A is V, we have to provide stirrup. A is V, total area of the legs shear links. So, we can have say for two legged 2 times that area of the cross sectional area of the bar provided, S V spacing of links. So, how many stirrups? We can write down number of stirrups cut by a 45 degree crack line. This is a crack equals say n say equal to, I can write down d effective depth by S V. So, what we can do it here in this case, the number of, if we have spacing S V and number of stirrups. So, I can get that this 45 degree crack we can get, because we are starting from the effective depth here, is equal to d by S V, the number of stirrups which we shall get here within this zone. That because we have to resist.
S V is not constant throughout the week, S V may change throughout the week.
No, we are assuming that in this case we are assuming that we are giving the same S B, because that for our calculation that we have to take care that S B same for the throughout the section, throughout the length where we are considering, otherwise we cannot provide. But we restrict ourselves, say we can go up to say 1/3 distance a certain spacing, and depending on the shear force available. So, we cannot just simply we cannot varying spacing we cannot provide, we have to provide certain spacing up to certain length, and then again we can say in the middle portion say shear force is less, and that is why we provide that different spacing. Okay. But when you are doing the calculation, then we have to take care this say spacing uniform. Okay. We can find out here the total shear resistance of the vertical stirrup system across the section is given by Vs equal to 0.87 times FOI ASV times number of stirrups d by SB, because already we have done. So, 0.87 Fy SB is the for the one say stirrup, which is say it may be 2-legged, 4-legged, that is taken care of in ASV, times that number of stirrups, that spacing on the basis of that we have already done say n. So, d by SB. So, we can write down here Vs equal to tau V minus tau C Bd. So, Vs equal to tau V times Bd, because already we have done tau V times Bd minus tau C times Bd, because this one we are getting from the depending on the longitudinal reinforcement. So, we shall get Vs equal to this one. So, we can write down tau V minus tau C Bd equal to 0.87 Fy SV times d by SV, which is nothing but this one equals this much. So, we can write down tau V minus tau C equal to 0.87 Fy ASV by BSV. So, tau V minus tau C equal to 0.87 Fy ASV by BSV. We can write down in a different manner. We can also write down the expression here, say ASV by SV equal to tau V minus tau C times B divided by 0.87 Fy. So, ASV by SV equal to tau V minus tau C be 0.87 Fy. What we can do, that means this side we can find, we know tau V, we know tau C depending on the longitudinal reinforcement, we know that B 0.87 Fy, because which particular reinforcement you are providing, grade Fe 415 or Fe 250. So, we know this side ASB, that means you are providing ASB, that we are choosing the bar diameter 8 millimeter, 10 millimeter, and also you are choosing the 2-legged. So, that means you know ASV. So, we can get SV. So, we can get SV and we can find out, and depending on the limitation, the restriction, we can provide that reinforcement, that spacing. So, this is the thing what we do. We can solve one small problem, I think, within a short time. So, what we shall do, let us take one example. Let us take the rectangular beam. B equal to 300 millimeter, D equal to 500 millimeter, VU 350 kilonewton, tensile reinforcement. Please note tensile reinforcement. I am repeating every time tensile reinforcement, not the compression, because that table 19 of IS 456, it gives on the basis of tensile reinforcement only, percentage of steel. That is 525 torr, concrete M20, steel Fe 415, and we have to design stirrups. So, what we have to do, design of stirrups for shear. Number 1, let us find out nominal shear stress. So, V u given as 350 kilonewton, tau V equal to V u by B d, 350 into 10 to the power 3 divided by 300 times, what about d? Let us take d equal to capital D minus clear cover minus 5 by 2 equal to 500 minus clear cover is not given, but we are assuming 25. Okay, we can assume, unless otherwise specified, we can assume certain dimension here. So, 25 by 2, that which comes as 462.5 millimeter. So, let us put it here 462.5, and which equals 2.5225 Newton per square millimeter. Okay. So, now we can calculate what about the tau c that we can calculate. Number 2, AST, that area of longitudinal steel, AST 5 times whole square equals 5 into 491, which comes 2455 square millimeter. What about then percentage of steel? P equals 2455 into 100 divided by 300 into 462.5, that effective depth, equal to 1.769%. From table 20, tau c max, maximum tau c max equal to 2.8 Newton per square millimeter. From table 19, for tau c, P 1.75, tau c for M20, I am just giving the part from table 19. So, for percentage of steel P 1.75, it comes 0.75. For 2, because I am taking 1.769, for 2, 0.79. So, this is the part of the table of table 19. So, where it comes P 1.75, 0.75 Newton per square millimeter. Let us write down this one, Newton per square millimeter. This is Newton per square millimeter. So, I shall get tau c equal to 0.79, let us make it elaborate, divided by 0.25 times 1.769 minus 1.75 plus 0.75. 0.75 is the one that for 1.75, which comes as very small, almost we can take the same one, 0.72 Newton per square millimeter. Okay. Just linear interpolation. In that segment, you take the linear interpolation and you do it. So, it is very simple. So, we can write down A is V A is V by SV equals, we can write down A is V by SV equals we have already noted down, we can go to that, excuse me, we can. So, for vertical stirrups, as per our code says, we can write down here let us write down first clause .4 for vertical stirrups. So, which comes as, it says VUS equal to 0.87 FY ASV times D divided by SV. So, we can write down this one, and this is given in page 73 of IS 456. So, we can write down as ASV by SV equal to VUS by 0.87 FY times D equals VU minus tau C BD divided by 0.87 FY D equals B times tau V minus tau C by 0.87 FY, the one which we have got it, which comes as 302.5225 minus 0.752, 2.5225, that is tau V, we have got it nominal shear stress, minus 0.752 divided by 0.87 times 415, that concrete, sorry, steel grade, and which comes as 1.471. So, ASV by SV equal to 1.471. What about ASV? How much is the ASV? So, ASV equal to 2-legged 2 into pi by 4, let us take it's 10 millimeter, because we can do trial and error. Let us take, I am taking say 10 millimeter. So, which comes as 157 square millimeter. ASV by SV we have already computed as 1.471. ASV equals ASV by 1.471, 157 divided by 1.471 equals 106 square, 106 millimeter. So, what about the spacing? Maximum, so let us say maximum spacing 0.75 D equals 0.75 times, how much is your D? So, D comes as 462.5 equals, so 0.75 into 462.5, 346.8 millimeter, and B not more than 300 millimeter. So, we have got 106 millimeter which is less than that. So, that means we have to provide 10 torr two-legged at the rate of 106 is not a good one. So, we shall provide 100 millimeter center to center. So, 10 torr two-legged at the rate of 100 millimeter center to center, that we shall provide. So, this is your that stirrup. Okay. So, this is your that how we generally calculate that your stirrup. So, if we summarize that what we have done, we shall get this VU from our calculation, from our analysis after doing the proper factor, all those things. We shall get the nominal shear stress using this formula and which our code permits. We know the longitudinal area of steel because already we have provided that reinforcement from the flexure point of view. Depending on that, we shall find out the tau c, that concrete contribution in shear resistance. We can find out depending on the percentage of steel, and which we shall get from table 19 of IS 456. We shall also get the maximum shear stress permitted for a particular grade of concrete. For this case, say M20 grade of concrete, this is M20 grade for M20, 2.8 Newton per square meter. If it is more than tau v, if it is more than this, then what will happen? Then we have to redesign the section from the shear point of view. That means, we have to change the depth of the section. After that, we can get the, we have already derived, also we can get the formula in clause 40.4 for vertical stirrups, the same formula which we have derived, and we can find out that ASB by SV 1.471 in this particular problem. Now, we shall choose that whether we shall provide 80 millimeter or 10 millimeter or 12 millimeter the stirrups, two-legged or three-legged, whatever the depending on the situation. We provide this diameter, we choose the diameter and that number of legs. Most of the cases it is two-legged. We can find out ASV and we can get that ASB by SB. On the basis of that, we shall check how much is the ASB permitted or computed. Now, we have restriction in our code that we should not be, in this case, we should not be more than 0.75 D, 346 millimeter or 300 millimeter. So, but in any way it is coming less than that. So, we have to provide that. So, which is coming, say we can provide safely 10 torr two-legged at the rate of 100 millimeter center to center, that we can provide. We shall continue with other problems, okay, with the stirrups also, inclined member, inclined stirrups also. So, this is the one, let us stop it here. Thank you.